Hello, my name is Anya Haverch, and in this video I will talk about uranium and depleted uranium discovery and application. Uranium was discovered in 18th century by German chemist Martin Heinrich Klaproth. While working in his laboratory, Klaproth analyzed the mineral pitchblende and precipitated a yellow compound. He believed it to be the oxide of a new element. Then he heated this compound with charcoal, and it resulted in a black powder that he thought was the new metal. He named it uranium after the planet Uranus that had been discovered 8 years before. However, Uranus is an ice giant and not a rocky planet. It does not have a lot of uranium, unlike some other bodies in the solar system. Pitchblende, the mineral that has been used for discovery of uranium, has been known since at least the year 79. The first successful isolation of uranium metal occurred in the 19th century by Eugene Mercier-Parigot, who heated uranium tetrachloride with potassium. There are three natural isotopes of uranium, and those are uranium-234, 235, and 238. This number is a mass number and presents the sum of protons and neutrons within the atom. Uranium-238 is the heaviest and the most common one, accounting for around 99% of natural uranium found on Earth. Uranium-235 is the only one that undergoes fission, which means that it can fragment under the effect of neutron. If we talk about radioactivity of uranium, then we have to mention that the Röntgen rays were discovered in 1895. Only a year later, Becquerel discovered the phenomenon of radioactivity by exposing a photographic plate to potassium uranyl sulfate. Later on, Marie Skłodowska-Curie recognized that some samples of pitchblende have a high radioactivity as pure uranium salts. And in late 18th century, Marie and Pierre Curie discovered two new radioactive elements, radium and polonium, that both can be obtained from uranium-238. If we talk about the use of pitchblende or uranium oxide, I already mentioned that it was known since the year 79 and used as a coloring agent for pottery glaze and to produce yellow-colored glass. Pitchblende has been obtained from silver mines ever since 15th century. The most typical color of uranium glass is pale yellowish green, so-called Vaseline glass, because of perceived resemblance to the appearance of commercially sold Vaseline at that time. The mixture of uranium oxide can vary in proportion, and color can vary from yellow and orange to dark green, depending on the temperature at which the material is dried. Higher drying temperature are producing a darker and less soluble material. Uranium was initially used for radium isolation. In early 1900s, radium was mistakenly believed to have health benefits and was included in various consumer products such as toothpaste, hair creams, even some food products. Of course, these uses were discontinued due to the health hazards associated with radium exposure. Over the years, uranium has had a variety of applications in photographic industry, but it was mostly used as a toner as it's used on this photo of Marie Curie. Replacement of silver with uranium was resulting in the image to change progressively from black to reddish brown. How much uranium would that end up in the final image would depend on how long the print was left in the toner and how dark the image was. Uranium's ability to undergo fission was discovered in the mid of 20th century. The mechanism of fission and its potential for releasing vast amount of energy was later explained, and it led to extensive research into nuclear energy and into development of nuclear weapons. Nuclear energy plants mainly use uranium-235 to generate heat and boil water into steam. When neutrons come into contact with uranium atoms split, releasing heat energy, and this occurs at a regular time and all the time in nature, but at a very slow rate. Nuclear reactors are able to speed up this process by slowing down the neutrons and increasing the likelihood that they will hit and split their uranium atoms. When uranium atoms split, they also release more neutrons, which can then go on and split additional atoms, ensuring a chain reaction that is called nuclear fission. Due to the nature of the nuclear fission process, nuclear energy plants do not burn any fuels, and therefore they do not produce smoke or generate greenhouse gases. Uranium has the largest atoms of the naturally occurring elements on Earth, making it more likely to split than other atoms. As mentioned before, uranium-238 could be converted into separate elements such as plutonium-239. It is also used for fuel and atomic weapons. So, to point it out, uranium is a key component in the production of nuclear weapons. It is also used to power naval vessels such as submarines. It has also a medical use that is based on medically useful isotopes. And finally, uranium is used for the production of depleted uranium that I will talk about in a while. Natural uranium typically contains only 0.72% of uranium-235, and the most reactors need a higher concentration of this isotope for their fuel. Therefore, the uranium-235 concentration is being artificially increased, even above 20%, and that is achieved through a process called enrichment. Uranium as it is can only be directly used in CANDU, that stands for Canada Deuterium Uranium, which is a type of nuclear reactor that was developed in Canada. This reactor is unique because it uses natural uranium and heavy water, both as its coolant and neutron moderator. Uranium dioxide is obtained through a series of chemical processes involving extraction, purification, and conversion of uranium ore. It is commonly used as nuclear fuel in reactors, especially in its pellet form. Concentrated uranium oxide with no less than 80% of uranium is called yellow cake. And yellow cake is not directly used in nuclear reactors. Instead, it serves as an intermediate material that is further processed in the nuclear fuel cycle. One of its main uses is to be chemically converted into uranium hexafluoride, UF6. And UF6 is necessary for the enrichment process where the concentration of uranium-235 is being increased to the desired level. Uranium-235 is the only isotope existing in nature in an appreciable amount that is fissile with thermal neutrons. Enrichment of uranium to over 97% has been accomplished, and there are two methods of enrichment, which are gaseous diffusion and gas centrifugation. The last one is considered as more modern. For many years, the old uranium that was mined was used for the production of nuclear weapons, but that stopped in 1970s. The onset of World War II and the subsequent Manhattan Project transformed uranium from a relatively obscure then element into a component that is critical for nuclear weapons development. The Manhattan Project was a secret US government research and development initiative during World War II that aimed to develop the first nuclear weapons. It was one of the most significant scientific and military efforts in history and led to the creation of atomic bombs that were used on Hiroshima and Nagasaki in 1945. The first uranium bomb, known as Little Boy, contained 64 kilograms of 80% enriched uranium, and the team at that time did not consider that it was necessary to test it before use. This slide shows uranium enrichment levels and their use. The uranium-238 remaining after enrichment is known as depleted uranium and is considerably less radioactive than natural uranium. Depleted uranium is either stored as UF6 or, especially in France and now also in Russia and in the United States, it is deconverted back to triuranium octoxide, which is more benign chemically and therefore more suitable for long-term storage. It is also less chemically toxic. This slide explains the uranium mining and conversion cycle from extraction of uranium ore and its direct use or processing stages and storage. And if we focus only on depleted uranium, before depleted uranium can be used in munitions, it must be converted from UF6 into a more stable form, such as uranium oxide or uranium metal. This conversion is typically carried out at specialized facilities. Once converted, depleted uranium can be processed to manufacture penetrators cores for munitions. This involves casting, rolling, and machining the metal into the desired shapes. And this process requires specialized knowledge due to the toxic and radioactive nature of depleted uranium. Thank you for your attention and listening.